Now, that map goes back to understanding crystallographic points and directions. And so the first place to start is going back to the unit cell. We talked about the unit cell being the building block, or almost that Lego block, for the crystal structures and the larger structures that we're going to be fabricating and looking more closely at. Now, if we want to start looking at these, we have to really look at what the unit cell is. And so we've done this before with typical labeling conventions. We looked at the unit cell. And so we know that there are the lattice parameters, A, B, and C, which are the distances of the cube. We know the orientation that we want to maintain, this X out of the paper, Y parallel, and then Z in sort of a vertical direction, and these three angles. So we know these unit cells. And so it leads us to, how do we define certain points? Now, as I start looking at a unit cell, first thing that comes to mind to me is, if there's anybody who's really an outdoorsman in the class, what you will tend to really think of is that looks like a grid square on a map. And so if you do orienteering or other types of what you might consider land navigation without a GPS, there are actually paper maps that some people use to find their way around, not the GPS in their phone or their car. And if you start looking at this, you can, within each of these unit cells, you can use these distances, these angles, particularly these distances, to be able to find specific locations within them. And we call these points. Now, there are a couple conventions that we use as we start looking at a unit cell and how it actually interacts. And within that, we have first points that we're looking at. Now, just like in any Cartesian coordinate system, which is basically what this unit cell is, we have an X, Y, and Z, and that is the order which we define these points. We cannot just, for the most part, arbitrarily take these points. We need to start at some point. And so when we look at points, we look at them in terms of these coordinates of Q, R, and S. And when we look at the unit cell, rather than worrying about what the atomic radius might be or the value of the lattice parameters for different materials, we simply take a fractional length along each of the axes. So in order to find a point, we need a Q, R, and S value. And within that, we can take a certain length of X, in this case, what we call along our A direction, and always think of it as a fraction. There will always be less than 1 for points in a unit cell. A direction in the R and a distance in the S direction. So if you think of the fractions, we can define this point pretty quickly. All values are less than 1. The position is defined by Q, R, and S. So let's take a look at this. So if we have a point, and before I move on too much further, when we have these points, when we're defining a point, you notice there are no parentheses, there's no brackets, there's no arrows, there's nothing around these 3 points. These 3 points sit alone. And that is one way to define what a point is. And within that, we see here that we actually have 2 fractions as well. 1/4, 1/1/2. Defines our distance in our x-axis, on our y-axis, and our z-axis. So in the image I took from the Callister textbook, we see that he defines it with a given values for A, B, and C along these actual distances. That is fine, but you already know, for the most part, what those distances are if we consider the unit cell to only be between 0 and 1. So if we start off with 1/4 in the X orientation, we go that quarter distance along that edge of the unit cell. We know our next step is going to be going the whole way across of 1 in the Y orientation. And then in the Z, we know is up 1/2. So at this point here, where P is located, we have our point, or this location that we're looking for within this individual unit cell. So at the end of the day, we can pretty quickly, as long as we know what these lattice parameter values are, determine what the actual lengths are. But these relative values can describe them pretty easily for us. So we move on. So we go from points, And usually the next step, if you go back to what your geometry classes were in high school, we start thinking of how do you define a vector? How many points do you need to define a vector? You need 2. And so we see the same thing with crystallographic directions. And usually within these, the vector will pass through the origin. Now, as we look at this, we see in this case that all of these vectors are located within the unit cell. That will not always be the case, because sometimes what is done in the Callister textbook is that he's not telling you which unit cell. He may draw this type of unit cell, but then turn around and say, well, that's not the origin I want to use. I want to use the origin here. So keep that in mind, and we'll see that as we go to other directions. But in this case, what we're really interested in is, let's start at the origin. So all vectors will pass through the origin, and they will continue through the crystal lattice. Length of the vector, same as we talked about before. It's in terms of the unit cell dimensions. But in this case, each of the numbers is multiplied by a common factor. There are no commas, but directions are enclosed by square brackets, as we see here. I will say that again because that's something you're going to be expected to know on the exam as we move forward, is that directions are enclosed in square brackets. Number 2, there are no fractions, because each number is multiplied or divided by a common factor, so they're always integers. Now, these are 3 of the easier ones to look at. Now, as I sort of said, how do you define a direction? You define a direction primarily by 2 points. The first point, which is always good for us, is always at the origin. So it's always at 0, 0, 0. So we're going to start with our point right there. Now, how do we determine what the 1, 0, 0 direction is? So that tells us the same thing as we saw with the points or locations, where that x tells us is 1. So we can go to that 1, but we don't stop there, because we need to define the point, the second point, based off what its y and z coordinates are going to be. In this case, they're both 0 and 0. And so a 1, 0, 0 direction will simply be along the x-axis. My question for you is, if the direction we're looking for is the 0, 1, 0, where would that be oriented? It would be oriented along the y-axis, because the 0 tells us there's nothing in the x direction. The 1 tells us it goes to the y, and the 0 for the z says it stays in the same plane. So the 1, 0, 1, 0 would be along the y-axis. Now the 1, 1, 0 we see stays on this xy plane because there's still no z component to it. So 1, 1, 0 will go between, and then 1, 1, 1 sort of hits on all 3. And so we see the second point in the direction sits up here in the corner. So we will draw something that's perpendicular, or actually across the entire unit cell, across that internal angle. So we can also identify, and this is where I was talking about with negative directions, and what you'll see as we start going in the book, where we still have square brackets, we still have 3 integers, but if you see a line above one of the integers, it tells you that that goes in a negative orientation, because we see the unit cell here, we see our typical Cartesian coordinate system, but there's a negative y, there's a negative x, and there's a negative z that can be associated with that unit cell. And we can project along all of them. So let's take the 1 and what we call 1 bar, 0 direction. So anytime you hear somebody say 1, 1 bar 0, or 1 bar 0, it means that those 2 orientations that we're interested in are going in a negative direction. So let's think about this 1, 1 bar 0. We're working with the direction. We start at the origin. So that's our first point in the 2 points of a line. So we go out to the 1 location on the x-axis. Now the 1 bar, or this negative 1 location along the y, we know we're not going to go to the right because that's a positive 1. So we would go 1 unit cell length over in the negative y direction. And since there's 0 in the z, we see that 1 bar 0 will be this green line here. Now, there are a number of other ways that this can be identified or at least illustrated on the plot. As I said, that orientation, we can typically keep that orientation in the middle. In some cases, when some of these are drawn, people like to be able to keep the direction within the unit cell. So in this case, we may move the origin over to here. And so for a -1 y direction, it would end up here. So from our origin here, our 1 point here, our 2nd point here, the lines would be there. And if we look, they're equivalent because they're both parallel to each other along that same plane. And so that's an equivalency that we'll talk about. And if we get into the families of directions and planes, we'll see that. Now, this is where we see that. So for some crystal structures, in other cases, they're non-parallel directions. They have different indices and they're actually equivalent. And we see that families are grouped together with this sort of arrow. So directions are square brackets, families of directions are these arrows. So directions in the cubic crystals having the same indice, they basically, if you have 1, 2, 3 in a cubic crystal, no matter what order you put them in, they are equivalent. So they will be in the same family. In a tetragonal system, that's not the case. So if we think about a cubic system, this makes sense because the cube is equal on all sides. A equals B equals C, they're all 90 degrees. So there's all this sort of equivalency with them. And so that's where we see these different types of families. And just as a note, families of directions have these types of arrows around them. Now, hexagonal crystals tend to get a little more complex with directions. What we tend to see, I'm not going to spend a lot of time on this, I want it to be something you identify. If we're in more materials or crystallography type class, we'll be spending a lot more time looking at symmetry in these directions within hexagonal systems. But in hexagonal systems, we tend to go from this 3-index system into what we call a 4-index conversions, and they can be adapted in this way. But just the thing that I want you to remember in this case is that in hexagonal crystal structures, we have 4 indices rather than just 3. We're going to stick with the 3 for this class.